Okay, let's have a look at this CIE paper 4 from 2017. Number 1, explain how a satellite may be in a circular orbit around a planet. Well, we know for circular orbit we need circular motion. So all we need for that is force of gravity between satellite and planet provides centripetal force. Okay. Earth and the Moon may be considered to be uniform spheres that are isolated in space. Bless them. Earth at radius r and mean density rho. Moon at mass m is in circular orbit, yada yada. Moon makes one complete orbit of Earth in time t. Show the mean density of the Earth is given by the expression this. So the very first thing that we always do is equate gmm over r squared. However, we are dealing with not r but nr squared. So we've got to be careful with that with this. Equals mv squared over, again, is nr. Okay, so I can see that one of these cancels, so we just end up with nr there. I can see that m's cancel as well. And we want the mass of the Earth in terms of density, so it's a sphere, so that's 4/3 pi r cubed. It is going to be r this time because that is r, times the density. Okay, so we have 4/3 pi r cubed rho divided by nr. Let's get rid of one of these r's already. And that's equal to v squared. Now v is given by 2 pi, well, it's the radius, so again it's going to be nr divided by the time. All of that is squared, so it's going to be 4 pi squared n squared r squared over t squared. So let's tidy this up. I can see that the r squareds are going to cancel, which is good. We don't have an r in here. 4s are going to cancel, so we're just going to end up with a 3 on the bottom here. One of these pi's is going to cancel as well. Oh, I'm missing my g from there. Whoops. So we're going to end up with g rho over 3n equals pi n squared over t squared. Putting things over to the other side, we can see that therefore 3 goes on top. 3 pi, 1, this n is going to go over here, n cubed over gt squared, job's a good one. So this is the first bit that we always go with, equating Newton's equation with centripetal force. Radius r of the Earth is that, and the distance between the center of the Earth and the center of the Moon is that. Period to the orbit is that. Use the expression in B to calculate rho. So we had rho equals 3 pi n cubed over g t squared. So we know all of these things, but what is n? So n is the radius of the path of the Moon in numbers of Earth radii. So therefore we want to have 3.84 times 10 to the 5 divided by the radius of the Earth. And that will give us our factor of how much bigger one is than the other. And that gives us 60. Seeing that they've gone to 3 sig figs, we better had as well, 60.2. But we want t in seconds as well. So, hey, we can just leave that until the end. So here we go. 3 pi times 60.2 cubed divided by g, 6.67 times 10 to the minus 11, and divided by, now we want all of this squared, so that's 27.3, that's days, times 24 hours, times 3,600 seconds, and that gives us a density of 5,540, if we're going to 3 sig figs, kilograms per meter cubed. 2 bar magnet of mass 180 grams is suspended from a free end of a spring, as shown here. Magnet hangs so that one pole is near the center of the coil of wire. Coil is connected in series with a resistance switch, which is open. Magnet is displaced vertically. It's allowed to oscillate. At time t0, magnet is oscillating freely as it passes through its equilibrium position. We can see that it starts at equilibrium. At time t3 seconds, the switch in the circuit is closed. A. Determine to 2 sig figs the frequency of oscillation of the magnet. Okay, so let's take not just one oscillation, but a few of them. Let's go 1, 2, 3, 4, 5. So 5 full oscillations is 6 seconds. So we could find out the time period by just dividing by 5, but let's just put it the other way around. 5 divided by 6, and that gives us 0.83 hertz. State whether the closing of the switch gives rise to light, heavy, or critical damping. Well, we can see that the amplitude is just decreasing gradually, so that is light damping. Calculate the change in the energy delta E of oscillation of the magnet between time t 2.7 seconds and time t 7.5 seconds. Explain your working. Whenever it comes to energy, we usually use the speed, and we want the maximum speed here, and that's going to be 2 pi FA. So if we're looking for a difference in energy between here and here, that means we are looking at a difference in amplitude. So delta E is going to be half mv squared. Okay, it's Vmax, but let's use v squared minus half mu squared. Let's say that's the beginning velocity. Of course, we can factorize this for half m. That's going to be v squared minus u squared. But again, that's going to be half m 2 pi f. Our first amplitude. Okay, I've got my v and u the wrong way around. It doesn't matter because we're just looking for a change in energy. So it's all of that squared. Take away the same for the other side as well. So again, I can just factorize for 2 pi f squared. So it's going to be a half m times 2 pi f squared. And then it's going to be one amplitude squared, take away the other amplitude squared. So ultimately, this ends up being, well, getting rid of the half and the 2 in there. So that's 2 times the mass, 0.18 needs to be in kilograms, times pi squared, times the frequency, 0.83 squared, and then we need our 2 amplitudes. Again, it needs to be in meters, so 0.015 squared, take away, I can see that that is 0.075. That gives me 4.1 times 10 to the minus 4 joules. 3. Digital transmission of speech may be illustrated using the block diagram here. State what is meant by a digital signal. A signal that consists of highs and lows opposed to a continuously changing signal. State the names of the components labeled X and Y in figure 3.1. Well, if we have the analog to digital converter here, because that's what ADC means, and we have a serial to parallel converter over here, we need the opposite over here. So it's a parallel to serial converter. And again, opposite over here as well. It's a digital to analog converter. Describe the function of the ADC. So you have this curvy analog signal going in, and then it samples it every so often. Samples signal at regular intervals and converts analog value to a digital value. So instead of a wave, we end up with squares instead, steps like that. Optic fiber has length 84 kilometers and the attenuation per unit length of the fiber is 0.19 decibels per kilometer. Input power to the optic fiber is 9.7 milliwatts. At the output from the optic fiber, the signal to noise ratio is 28 decibels. Calculate in decibels the ratio input power to optic fiber over noise power at output of optic fiber. First things first, we need to find out just how much attenuation is happening over the 84 kilometers. So attenuation 84 times 0.19, and that is 16 decibels. So we have 16 decibels attenuation over the whole fiber. And because we're dealing with logs here, we just have input power to optic fiber divided by noise power output of optic fiber. So this is equal to this 16 decibels plus the 28 decibels. That gives us 44 decibels. That's the thing about this log scale. Because it's a log, we can add up the values. Part 2, calculate the noise power at the output of the optic fiber. So decibels are equal to 10 times log to the base 10 of the ratio of powers. Now we have been given the input power, which is 9.7 milliwatts. So this is 9.7. We can keep it as X. It's just a ratio. We're trying to find this power here. So we know that 44 equals 10 log 9.7 over P1. So that's 4.4 equals log 9.7 over P1. Therefore, 10 to the 4.4 equal to 9.7 over P1. Swapping these two round, this power is equal to 9.7 divided by 10 to the power 4.4, and that gives us 3.9 times 10 to the minus 4. However, if this was milliwatts, but we're looking for watts, that means that that's going to be 3.9 times 10 to the minus 7 watts. Question 4. Describe the motion of molecules in a gas according to the kinetic theory of gases. It is random with equal distribution of velocities in all directions. Describe what is observed when viewing Brownian motion that provides evidence for your answer in A. We see it with small specks of dust or smoke. These move in random directions. We can say that they zigzag due to collisions with air particles or gas particles. At a pressure of 1.05 times 10 to the 5 pascals at a temperature of 27 degrees, let's turn this into Kelvin already. 1 mole of helium gas is a volume of this. The mass of 1 mole of helium gas, assumed to be an ideal gas, is 4 grams. Calculate the root mean square speed of an atom of helium gas for a temperature of 27 degrees. So we can say that half mv squared, okay, where v is CRMS, that is equals to 3 halves kT. Or if we've been given the mass of a mole, then we can say that half big mv squared, where m is the mass of the mole of gas, is equals to 3 halves RT. Halves disappear, and we're looking for V. So V is the square root of 3 RT by M. And that is equal to the square root of 3 times 8.31 times 300 divided by 4 times 10 to the minus 3. And that gives us 1.3. Let's go with 1.4. Seeing that they've gone to 3 sig figs, we will too. 1.37 times 10 to the 3 meters per second. Using your answer in 1, calculate the RMS speed of the atoms at 177 degrees. So plus 273, that's going to be 450 Kelvin, as opposed to 300, which we had a second ago. All right, so looking at the equation above, we know that obviously half m, well, let's call it c squared, equals 3 halves kT. So we can see that c squared is proportional to t, or rather c is proportional to square root of t. So we can say that c1 over root t1 equals c2 over root t2. We're looking for c2, so let's take this over the other side. So we end up with a second speed of the initial speed, which is 1.37 times 10 to the 3 times the ratio of the square root of the temperatures, and I can see that's going to be square root of 1.5, and that gives us 1.68 times 10 to the 3 meters per second. 5. Alpha particle is traveling in a vacuum towards the center of a gold nucleus, as illustrated here. Gold nucleus has a charge 79e. Gold nucleus and alpha particle may be assumed to behave as point charges. Thank goodness, at a large distance from the gold nucleus, alpha particle has an energy 7.7 times 10 to the minus 13 joules. Alpha particle does not collide with the gold nucleus. Show that the radius of the gold nucleus must be less than 4.7 times 10 to the minus 14 meters. Okay, so we're looking for distance of closest approach. And it's one of those things that people always find difficult for some reason, but literally it is just potential energy is equal to kinetic energy. Here the alpha particle has kinetic energy, and when it gets to this point and it turns round, then it has no kinetic energy. It's all turned into potential energy. So here we go. We can say that EK, the kinetic energy that it has, is equal to the potential energy, and we know that that is K Q1 Q2 over R, and R is the distance of closest approach here. K is 1 over 4 pi epsilon 0. K is a nice little shortcut. It's 9 times 10 to the 9. It saves you a little bit of time. So let's swap these two things over. So that means that the distance of closest approach here is going to be 9 times 10 to the 9 times 79 times 2, because it's got 2 protons, the alpha particle does, times, well, we want that E in there, but it's got to be squared. So I'm just being a bit clever with my maths here, saves me putting extra stuff into the calculator, divided by the energy, 7.73 times 10 to the minus 13. So let's see what we end up with, shall we? That's equals to 4.7 times 10 to the minus 14 meters. Jobs again. B, determine the acceleration of the alpha particle for a separation of that between the centers of the gold nucleus and of the alpha particle. So we know that F equals ma, so A is F over m. But what is the force on the alpha particle? It's equals to K QQ over R squared. So let's say over mr squared. So again, we can take this top bit here, 9 times 10 to the 9 times 79 times 2 times 1.6 times 10 to the minus 19 squared. Divide that by the mass of an alpha particle is 4 times 1.67 times 10 to the minus 27. So 3 sig figs, that's the mass of a proton and a neutron. Then times that by the separation, 4.7 times 10 to the minus 14. That's got to be squared as well. Okay, big calculation. Let's make sure that we put it all in correctly. We end up with a very big acceleration of 2.5 times 10 to the 27 meters per second squared. In an alpha particle scattering experiment, the beam of alpha particles is incident on a very thin gold foil. Suggest why the gold foil must be very thin. Well, if you have multiple layers of these protons, then you're more likely to get an alpha particle coming in and then pinging off multiple nuclei. So we only want each alpha particle to interact with one nucleus. So ideally need alpha particles to interact with just one nucleus. 6. Comparator circuit is designed to switch on a mains lamp when the ambient light level reaches a set value. An incomplete diagram of the circuit is shown here. A relay is required as part of the output device. This is not shown in figure 6.1. Explain why a relay is required. It's because this op amp here only has low output voltage or power, but the lamp needs a high voltage. Figure 6.1, draw the symbol for a relay connected in the circuit as part of the output device. So we have the little coily bit, and then we have our switch that it closes. Although you're going to draw yours much neater with a ruler and a pencil. Describe the function of the variable resistor RV. So with this variable resistor, you can physically change yourself the voltage at which the lamp turns on and off at. So voltage which lamp turns on at can be varied. What's the purpose of the diode? To ensure a current only flows in one direction through the op amp. C. State whether the lamp will switch on as the light level increases or as it decreases. Explain your answer. So let's think about this logically. If the light level increases, resistance of LDR decreases. Therefore, voltage across the LDR also decreases. Therefore, V dash, we can say that's PD coming into here increases, and when it's bigger than V plus, it's going in here, output from op amp is negative, and that's going to be minus 5 volts. It's either plus or minus 5 volts, isn't it? Therefore, light turns on. 7. Electron having charge minus Q mass m, accelerated from rest in a vacuum through PdV. Electron enters region of uniform magnetic field. Okay. Uniform magnetic field into plane of paper. So it's going in. Direction of the uniform magnetic field is into plane of paper. The velocity of the electron as it enters is normal to the magnetic field. Fine. Explain why the path of the electron in the magnetic field is the arc of a circle. Force due to magnetic field is perpendicular to the electron's velocity, therefore provides centripetal force, and an electron undergoes circular motion. B. Show that the magnitude P of the momentum of the electron as it enters the magnetic field is given by this. When it comes to electrons being accelerated by a PD, the energy that it has at the end is EV, And what kind of energy is that? It's kinetic energy, so half mv squared. But they've given us Q instead, so we're just going to say QV. This is one of those things that sometimes catches people out. So let's take the 2 over the other side first. So we have 2QV equals mv squared. Now we know that mv is the momentum. So we can say that this is equal to pv, can't we? And so we can say therefore that the momentum is 2q big V over little v velocity. However, that doesn't give us this though, does it? So basically what we need to do is multiply the whole thing by m. So let's get rid of that, and we end up with 2q big V is equal to p squared. So it's mv, but divided by a mass. So you can see that's mv squared, mv all squared divided by m. That gives us mv squared. And so putting this over the other side, we end up with p squared equals 2mqv. Therefore, p equals the square root of that. Potential difference, V is 120 volts. Radius R of the circle is 7.4 centimeters. So 0.074 meters. Determine the magnitude B of the magnetic flux density as per usual. BQV, little v that is, don't get confused with the V's, equals mv squared over R. See that one of those cancels. But can you see that we've actually got our mv from earlier? So what we can do is put that in instead. So BQ equals P over R. We're looking for B. Therefore B equals P over QR. And P is this square root of all this jazz here. So B is equal to the square root of 2mq big V over QR. You could tidy this up by sorting out the Q's, but I'm not going to bother. So that's going to be square root of 2 times this electron, 9.1 times 10 to the minus 31, times 1.6 times 10 to the minus 19, times 120 volts, divided by 1.6 times 10 to the minus 19, times this radius. There you go, popping that all into my calculator. Pretty much bang on 5 times 10 to the minus 4 Teslas. D, potential difference is increased. The magnetic flux density B remains unchanged. By reference to the momentum of the electron, explain the effect of this increase on the radius R of the path of the electron in the magnetic field. So looking at this here, we can see that R is equal to the momentum divided by BQ. So we can see that R is proportional to P. However, P is proportional to root V. So if you double the voltage that it's accelerated, the momentum goes up by root 2. So that means the radius is proportional to the square root of the voltage as well. Therefore, as V increases, R increases. 8. Explain the main principles behind the use of nuclear magnetic resonance imaging, NMRI, to obtain information about internal body structures. So the first thing you need is a strong magnetic field, and the whole point is that there's nuclear magnetic resonance because the nuclei rotate. The posh word is precess, about direction of the field. Radio frequency pulse is applied. The frequency is same as frequency of precession. This causes excitation. When nuclei relax, radio frequency pulses are emitted and detected. This allows the position of precessing nuclei to be obtained. And then we say that images are processed as slices of the internal body. 9. A simple transformer is illustrated here. State whether the transformer has an iron core rather than having no core. Well, the core, we know, guides the flux round to the secondary core, so we can say that it reduces loss of flux. Explain why the core is laminated. Reduces eddy currents in core, and therefore power loss due to heating. By reference to the action of a transformer, explain why the input to the transformer is an alternating voltage rather than a constant voltage. Nice and easy. AC produces fluctuating magnetic field in core. Changing field induces AC in the secondary coil. If DC used, secondary coil does not experience changing flux, therefore no current or EMF induced. 10a, 1. What is meant by the hardness of an X-ray beam? Hardness is the penetrating ability of a beam, and this is linked to energy of photons. State how the hardness of an X-ray beam from an X-ray tube is increased. Well, to produce X-rays, we need to fire the electrons at the metal plate at a faster speed, so we increase accelerating PD of electrons. Same parallel beam of X-ray radiation is incident separately on samples of bone and muscle. Data for the thickness X of the samples in bone and muscle, together with the linear attenuation coefficients mu of the radiation in bone and in muscle, are given here. Determine the ratio intensity transmitted through bone over intensity transmitted through muscle. So we know that intensity over original intensity is equal to e to the minus mu x in this case. So if it's the same beam, then this stays the same. So we're looking for intensity over intensity. So I bone over I muscle is equal to e to the minus mu of bone times the thickness of the bone divided by e to the minus mu of the muscle times x of muscle. So let's put that all in. So that's minus 2.9 times 1.5 divided by e to the minus 4 times 0.95, and that gives us 0.58. 11. Beam of light consists of a continuous range of wavelengths 420 to 740 nanometers. Light passes through a clouded cool gas, yada yada. Spectrum of the light emerging from the clouded cool gas is viewed using a diffraction grating. Explain why this spectrum contains a number of dark lines. Well, it's because the photons, or incident photons, interact with electrons in the gas molecules. Only photons of certain wavelength, certain or specific frequency, let's say, or energy, can be absorbed by raising electrons to a higher energy level. Now, there is one more thing that we can add on to the end of this. Yes, they get absorbed, but these electrons do de-excite. But when the electrons do de-excite, instead of all the photons being fired out in the same direction as the photons that are just being transmitted through, photons are released in all directions. They're emitted in all directions. Okay, some of the electron energy levels of the cloud are represented here. Light of wavelength 420 nanometers has a photon energy 2.96 electron volts. Calculate the photon energy in electron volts of light of wavelength 740 nanometers. Now we could go E equals HF, or in this case HC over lambda, and we could do it from there, but we'd have to convert it into joules and all that jazz. Or we can just say, look, we've been given one wavelength and an energy already, so we can say that energy is proportional to 1 over the wavelength. So we can say that E1 lambda 1 equals E2 lambda 2, and we can just keep all our numbers as nanometers and electron volts. We're looking for energy 2, so let's put this over the other side. So the energy 2 ends up being 2.96 times 420 divided by 740. And that gives us 1.68 electron volts. Use data from 1 and your answer to 1 to show the changes in energy levels giving rise to the dark lines in part A. Okay, so we have the maximum and minimum wavelengths and therefore the maximum and minimum energies. We're looking for any energy difference that sits between 2.96 and 1.68 electron volts. So we can't do anything between here. So there's nothing between 13.6 and 3.4. What about 3.4 to 1.5? What's the difference there? Well, that's going to be 1.9 electron volts, and that does sit between there. So that's going to be one of them. What about from 3.4 to 0.85? That gives us 2.55. Yes, that's still within our range, so we can go up to here. What about 3.4 to 0.55, 0.54 rather? That's 2.86. Yes, that can happen as well. What about to 0.38? 3.02. No, we're outside of our 2.96 electron volt range. So we can't go from there to any higher. We can't go from 1.5 to anything else, otherwise it's going to be less than that 1.68 as well. So these three absorptions are what result in our dark lines. 12. One possible nuclear reaction that takes place in a nuclear reactor is given by the equation this. Data for the nuclei and particles are given here. Determine for this nuclear reaction the value of X. So we're looking for the number of electrons that are being produced in this reaction. So we know that electrons basically have no mass compared to protons and neutrons. So let's have a look. We have 92 protons, no protons here. So 92 going in, 42 and 57. We have 99 protons. So the question is that we've gone from 92 to 99 protons. How have we done that? Well, we've gone through 7 beta decays, as it were, all in one go. So there's going to be 7 electrons being produced. B, show that the energy equivalent to 1 U is 934 mega electron volts. So look at on our formula sheet, we can see that 1 U in kilograms is equal to 1.66 times 10 to the minus 27 kilograms. And if we want to know the energy, the rest energy of that, it's E equals mc squared. So that's going to be 1.66 times 10 to the minus 27 times 3 times 10 to the 8 squared. That gives us 1.494 times 10 to the minus 10 joules. However, turning that into mega electron volts, we need to divide that by 1.6 times 10 to the minus 13, because it's mega electron volts. That gives us 934 mega electron volts. Okay, calculate the energy in mega electron volts released in this reaction. Give your answer to 3 sig figs. Okay, so we need to find the mass defect. We need to find out the difference in the mass before and afterwards. So the difference in mass is going to be the mass of this, so that's 235.123, plus our neutron, which is 1.00863, take away the mass of everything afterwards. So that's going to be mass of the molybdenum, 94 point, plus the mass of the lanthanum, which is 138.955, plus 2 more neutrons. So actually what we can do is just get rid of one of the neutrons from that side and just have 1 neutron over this side, plus 7 lots of electrons. So that's 5.49 times 10 to the minus 4. Okay, big calculation. You don't want to mess it up putting it into your calculator. So here we go. Tell you what, let's just do this side first. So 94.945 plus 138.955 plus 1.00863 plus 7 lots of 5.49 times 10 to the minus 4. That gives us 234.9, but then we need to do 235. Whoops, nearly messed that up. 0.123, take away our answer, and we end up with a mass defect of 0.210527 U. But we know that we can just times that by 934, and we end up with 197 to 3 sig figs mega electron volts. Suggest the forms of energy into which the energy calculated in B2 is transformed. Obvious one, the things that come flying out have lots of kinetic energy. Kinetic energy of products. But also we know that we have radiation being produced as well. And so it's usually from nuclear reactions, gamma radiation. We can say photon energy. That's it.